All right, welcome everybody. Today we're going to continue talking about Bernoulli's equation, and the homework assignment that you've got related to the more complicated Bernoulli's type questions. Homework 7 is due a week from today. That's going to include some questions related to Pitot tubes, which we're going to get into today, and then irrotational flow we'll address on Thursday this week. I also want to draw your attention to the announcement that your next quiz is on Tuesday the 29th, and so that's a week from today. The format of that quiz will be largely the same as the first, where it's just a single question. My intention is that the quiz will take between 15 and 20 minutes for you to complete. I'll provide the equations for that, so you don't need to prepare any kind of a formula sheet. So, any questions on the announcements? Yeah.
So it's going to cover all the materials up to the Thursday's lecture?
Correct, yeah. It's going to be from the first midterm until Thursday's lecture, so class 18. Any other questions? All right. So a bit of review related to fluid acceleration. Unsteady flow is caused by what kind of acceleration?
Local?
Right. So unsteady flow is when conditions are changing over time. And so local acceleration is the acceleration type where a fluid is changing with respect to time. Convective acceleration causes what flow type?
Steady?
Non-uniform, right. So when we have convective acceleration, that's the acceleration where velocity is changing with respect to position. And so that is the definition of non-uniform flow. And then the equation that describes changes in pressure caused by local acceleration, that's Euler's equation. So I just want to modify something I said a moment ago. So the quiz that you're going to have on Tuesday will be one problem-solving question, but I might throw in some definitions as well. All right? Might. All right.
How does it hurt?
All right. Well, just to review, basically what we've been talking about so far with Bernoulli's equation is that when there's an increase in velocity, there's a decrease in pressure. And so I've sketched this before on the whiteboard, but here's an animation that kind of shows in an interesting way that the air particles that move on the top of the wing in an airfoil do so at a faster velocity than the particles under the wing. And this is exaggerated from effect. I don't think that the velocity on top of the wing is 3 times as fast as the velocity under the wing, as is kind of implied by this illustration. But what this does effectively show is that we have lift from a wing because of the difference in pressure. The pressure is lower on the bottom part of the wing, and the pressure is lower on the top of the wing. The pressure is higher underneath, and that net difference in pressure is what causes the lift. So we're going to watch a video recording that was made in 1969. The picture quality is not the best, but it's still kind of got a really several interesting physical applications. It's going to take about 10 minutes, so let me pause the recording here.
Based on the Bernoulli's equation and what he did with the balls.
Yeah.
So eventually the ball will finally. I noticed the ball was changing in height as it was being blown up, but eventually it reached a point where it does not move in a height change. So if there's 2 pressures acting on it, then that means eventually the height will equal 0. A change in height, the height of the pressures will equal 0.
Are you talking about when he was changing the angle?
Well, like on the toy car, the ball in there, it's like it was blowing up, and the ball was moving a little bit up and down.
Yeah.
But eventually it stays still to the same vertical height. That's what I was like talking about.
Yeah, I'm not sure why it was varying. It may be the fan inside just wasn't blowing the same velocity the whole time, you know, because it was just a wind-up fan.
Yeah, and well, I also noticed when the pressure, the air pressure that he was blowing out, that the ball was like moving in that same way as well.
Yeah, it could be that, you know, he was a finger-operated valve, so it's maybe not the same velocity.
So it's not the same constant velocity.
Yeah, I think so.
Okay.
One of the applications of Bernoulli's equation is using a device to measure the flow of fluid, specifically in this case a liquid. What you can do with a stagnation tube is make use of the fact that when you intersect a streamline for a fluid that has velocity, when the liquid reaches that stagnation point, all of the energy that existed as velocity upstream is instantaneously turned into additional pressure at that stagnation point. And so what you can see here with the stagnation tube is that you can think of this as just a straw that's been pointed in the direction of the oncoming fluid. And so if you put the straw down in the liquid, the water level is going to rise above the natural water surface. There's this additional rise here to the distance of L, and the purpose of that, or the cause of it, is simply because there's more pressure just on the inside of the tube. They've been a little bit sloppy here in labeling where is location 2. Here in their sketch, it looks like location 2 is on the outside of the stagnation tube, but let's just say for sake of illustration that location 2 is just on the inside of the tube. What we know is that conditions in that tube are static. You know, the water level, as the velocity increases, the water level is going to start at equal to the surrounding water, but as the velocity goes up, this L will increase and then it's going to reach an equilibrium. And this can be explained by starting with the Bernoulli equation applied between 2 points that are on the same elevation. And so they have the same elevation between 1 and 2, and so we've just taken the z term out of Bernoulli's equation. And so what this is saying is that between the two locations, the pressure term, and this is sometimes called kinetic pressure when we write it in terms of having the same units as pressure. So instead of, you know, having pressure head, velocity head, and elevation head, here each term is written in terms of pressure. So we can rearrange this when we have that the velocity at 2 is 0, because inside the tube conditions are stagnant, meaning that there's static conditions with no flow velocity on the inside of the tube. So if you cancel out the V2 term from Bernoulli's equation, you can rearrange it to solve for the unknown velocity at 1. And what this is saying is that the velocity at 1 is equal to the change in pressure between 1 and 2 multiplied by 2 divided by the density. So the pressure at 1 is just related to the depth. So even though the fluid is moving sideways, we can approximate the pressure at 1 with the hydrostatic equation. The depth times gamma will give us the pressure at 1. At 2, though, we have to apply the hydrostatic equation starting here, where it's open to the atmosphere, and so the pressure at 2 is going to be the unit weight, and then the applicable distance is the depth to that location plus the distance above the water line that the water's rising to because of the stagnation point. So this is just another way for us to understand what's the pressure at 2, and the reason why they're different is, remember, some of the velocity that was at 1, that energy that was wrapped up as velocity, has to go somewhere when this streamline intercepts the stagnation point. And so that extra energy is immediately transferred into additional pressure. It can't transfer itself into additional elevation, and it's not going to, you know, if the only 3 terms is elevation, pressure, and velocity head, and so the velocity that is lost at the streamline intercepting the stagnation point goes into additional pressure. So we can rearrange this and substitute in the 2 definitions for the pressure, and after canceling out like terms, what it simplifies to is that the velocity at 1 is equal to the square root of 2g and then L, the distance above the water line, that how high the water is going to rise inside of the stagnation tube. Now there's a limited number of applications where this would be useful. This might potentially be useful in a boat if you wanted to know your velocity relative to the water. But then you'd have to have some sort of a tube that you could look at, and it would need to be calibrated to velocity. So instead of stagnation tubes, it's more common to use pitot tubes. But just to get some experience with this equation, let's use the illustration here that we have a stagnation tube, and we're designing a stagnation tube that we're going to use it to measure velocities as high as 2 meters per second, and we want it to be down in the water a depth of 0.5 meters. So how long of a tube would we need if we plan to measure that velocity of 2 meters per second, which is going to cause L, and then we're going to measure at a depth of 0.5 meters from below the water surface down to a depth of 0.5 meters. Okay, so I've sketched on the whiteboard that, if we're thinking in practical terms, you'd maybe want to have a little bit of extra length above where the water surface is going to be, and you'd need some length to make the bend so that instead of being vertically oriented, it's horizontally facing. Because if it's vertically oriented, then you wouldn't be intercepting a streamline. If we just had a straw that was going straight down into the fluid, it wouldn't have the same effect of it intercepting that flow velocity. And so if we do the calculations here, we get that L, the distance above the water line, is 0.204 meters, and we said it was going to be measuring at a depth of 0.5 meters, so at the very least it needs to be 0.704 plus the amount at the top and enough to make the bend underneath. So that's the idea of a stagnation tube. Now, just like when we were talking about manometers and piezometers, because of the practical limitations of stagnation tubes, such as that they're more useful for liquids than for gases, and the fact that it has to be open, it's better to use pitot tubes. And so a pitot tube is a little bit more sophisticated, and let me explain how it works. You're measuring the pressure at two different locations. And so assume for a minute that we have a fluid that is passing upward, and so this gas or liquid, it can work for either, is going to be intercepting this tube device, and at 1, if you notice how this is facing the flow, we're going to have that same stagnation effect at location 1. And so this velocity is going to stop when it reaches location 1 because inside of the tube conditions are stagnant. And so there's going to be a little bit of extra pressure at 1 because the streamline has been intercepted. But now look, follow this tube through and notice that it's connected to the stagnation pressure tap on a pressure gauge. And so at location 1 the pressure is going to be a little bit higher than at location 2. And so now the fluid that passes along the side of the pitot tube, here at location 2 where there's that opening that if you follow it to the side is connected to the other side of the pressure gauge, what we call the static pressure tap, it's not intercepting the stream. And so there isn't the additional pressure at location 2 related to the velocity. Location 2 is just measuring the ambient pressure. And so there's going to be a difference in pressure between 1 and 2. And assuming that there isn't that much pressure difference having to do with an elevation change, because strictly speaking, if you look at location 2 is higher in Z than location 1. So, I mean, in practical terms, it may be a centimeter or 2 centimeters apart on an actual pitot tube. But that vertical elevation difference is so minor that we usually neglect that effect, and we just say that the pressure difference as a whole is related to the fact that location 1 has a stagnation effect, location 2, because that opening isn't receiving the streamlines. They pass right by it. It's only measuring the surrounding ambient pressure. So if we consider the entire Bernoulli equation, what we see is that if we rearrange it based on the fact that there's no velocity at location 1, so cancel out the V1 term, what we can rearrange is that the pressure plus gamma z at 1 minus the pressure plus gamma z at location 2, and then we've divided by 2, multiplied by 2, divided by the density, because of if we're wanting to solve for the velocity at 2, and that's what the main application of pitot tubes is, to measure the flow velocity in pipes or on airplanes. And so we've rearranged this to solve for an unknown velocity by measuring the piezometric pressure difference between the two locations. I've already kind of told you that although this, strictly speaking, is to measure the difference in piezometric pressure, the elevation effect is usually pretty minor. And so what we're really measuring in practical terms is just the difference in pressure between those 2 points. So let's try out an example here. Let's say that we have a gauge that has a maximum pressure differential of 7.5 kilopascals. It can accurately measure from 0 on the low end up to 7.5 kilopascals. Now this time I've shown the pitot tube is oriented horizontally, because that's how they usually are in aircraft. Here it's showing an actual pitot tube, and it's probably tough to see because it's so small on the screen, but there is a small hole that's barely visible on the side of the pitot tube. So there's they're at the same elevation, the 2 openings, 1 and 2. If we assume that air has a density of 1.2 kilograms per cubic meter, what we want to know is what's the maximum airspeed that we could quantify with this pitot tube. We're wanting to know it in terms of kilometers per hour. So with a pitot tube connected to a pressure gauge that's able to have a maximum difference in pressure of 7.5 kilopascals, what is going to be the velocity at location 2? Remember, the way it works is we're canceling out V1 because location 1 is where the stagnation occurs. All right, so I'm going to pause for a moment, give you some time to think this over, calculate, check with your classmates, and try and find what is V2. All right, so this pitot tube is horizontally oriented, which means that the 2 elevations are equal, and the velocity at 1 is 0. Well, just inside the mouth of the pitot tube is 0. At 2, it's moving along, and so here we have Bernoulli's equation, and we can drop out the elevation terms. We can drop out the V1 term, and so all that's left is, on the left, some change in pressure is what is caused by this velocity, and so you'll get 111 meters per second, and then to make the conversions to kilometers per hour, you have to convert to how many meters there would be in an hour, so you're multiplying by 3,600, and then from meters to kilometers by dividing by 1,000. So 402.5 kilometers per hour. All right, so that's the functionality of a pitot tube, and sometimes we use them not just in gases, but pitot tubes can also be used to quantify the flow velocity in a liquid. And so this example is imagining the idea of what if you put a pitot tube into a pipe. Let's say, for instance, a pipeline that's carrying kerosene. And in this pipeline, the flow is going downward. And so we have the pitot tube pointing upward to intercept the flow direction. So as with before, there's going to be more pressure at 1 than there is at 2. And so if we follow this pitot tube down, this side of the pitot tube where there's the extra pressure is related to location 1. This end is on the outside at location 2. So we're measuring it with a manometer, and the manometer has mercury as the manometer fluid, but then it has kerosene on the rest of the manometer. And just to refresh your memory about the manometer equation, with manometers you can have the change in piezometric pressure measured by the deflection multiplied by the difference in piezometric pressure. Excuse me, the deflection multiplied by the difference in unit weights. All right, so here what I'm suggesting is that as a first step, what you should do is write the manometer equation starting at 1 and going through the tube until you get to location 2. And that's something that we've done before, is just basically say P1 plus and then some distance multiplied by the unit weight of whatever liquid is inside of the static area. And so we're going through the center of the pitot tube, and so it's static conditions inside the pitot tube, and all of it is all of it is kerosene except for this section, which is mercury. And so say P1 plus, and then the distance will be Z1 minus Z2 of kerosene. Then you're going plus L multiplied by gamma of kerosene, and so on and so forth, minus for when you're going up through the fluid, and then is equal to P2. So rewrite the manometer equation, then rearrange the manometer in terms of P sub Z. And remember that the definition of P sub Z is P plus gamma Z. And so P sub Z1, that means P1 plus gamma Z1. All right, so I'm suggesting that you rearrange in these terms, and then if this has a deflection of 18 centimeters, then what does that say about the flow velocity of kerosene inside of the pipe? All right, so maybe you already remembered the pitot tube. Excuse me. Maybe you already remembered that in a differential manometer, the change in piezometric pressure is just the deflection multiplied by the difference in the unit weights. But even if you don't remember that key fact, you can always kind of prove it to yourself by applying the manometer equation between the 2 points of interest. And so between 1 and 2, we can't apply the hydrostatic equation outside of the pitot tube because, here in the pipe, conditions are, the kerosene is flowing. But inside the pitot tube and through the manometer, it's static. And so what we can say is that we start at location 1 and we've got some pressure there. Pressure increases down through the kerosene portion of the pitot tube, and manometer decreases as we go up through the manometer fluid and then decreases the rest of the way to get to location 2. So expanding that out, canceling like terms and grouping in terms of piezometric pressure, we just get that the change in piezometric pressure is this deflection multiplied by the difference in the unit weight. Now, when we used differential manometers previously, the differential manometer was connected to 2 different openings in the same pipe, an upstream opening and a downstream opening. So it was a little bit different than here where it's just connected to the pitot tube. In that previous case when we were looking at differential manometers, the downstream segment, the liquid level was higher because the pressure was lower. What you remember about a differential manometer is that if the flow velocity is 0, then the two sides of it are going to be equal. You know, that deflection only sets up when there's fluid moving through the pipe because there's a change in pressure. And so what the differential manometer in this case is measuring is the energy loss due to pipe friction. So even if we incline the pipe, if we were going to have an inclined pipe, then there would still be no deflection if the fluid isn't moving. And so here's just another differential manometer. So let's say that it's full of fluid, but the velocity is 0. So if there's no flow going through the pipe, then it's level. But then as soon as fluid starts going through the pipe, the downstream segment is going to have less pressure. Even though it's at a higher elevation, what the differential manometer is measuring is the pressure change that's due to pipe friction. And so strictly speaking, it's measuring the change in piezometric pressure, not just the change in pressure. If it was measuring the change in pressure alone, then it wouldn't be level when the flow velocity was 0. But it is, and it only sets up a difference in the elevation when the fluid is moving. So here, how does that relate to this case? Well, if we think about the difference in pressure between location 1 and location 2, even though they are close together, we've kept track of the z's here between, you know, when we're deriving the manometer equation from the hydrostatic equation. We can keep track of the difference in elevation between 1 and 2, and that's accounted for by what the manometer is measuring. The manometer is just measuring the pressure difference that's caused by the intercepting of the streamline at location 1. So that once we take this equation and substitute it into the Pitot tube equation, and so the Pitot tube equation is, it's just really the Bernoulli equation. It's not a new equation. It's just the Bernoulli equation that we've rearranged so that V1 is 0. Now we have to calculate some of these density, unit weight from the given specific gravities, so that when we substitute it all together, what we'll see is that the velocity at 2 should be 7.47 meters per second. Now this last piece here, which density do you use? Because I don't think that that was necessarily specified here in the formula, to use the kerosene density. And that's, we used kerosene because it's kerosene that's between 1 and 2, both on the outside of the pipe and inside the Pitot tube. It's kerosene, so that's the density that you're using in the formula. So by a show of hands, how many people got 7.47 meters per second? Good. All right. Any questions about that example? All right, so I saw some of you in lab yesterday. I'll see the rest of you today. Well, most of the rest of you today. Hopefully we'll have fewer equipment issues than we did yesterday.
What happened?
Oh, we got wet yesterday. We got sprayed.
That must have been fun.
Don't worry, I found good duct tape, so probably today it'll be fine.
Now,
So I'll see you then.
Inventory meter?
I couldn't make it to the lab yesterday. Is there a way I can come to the civil engineering lab
Sure.
today?
Yeah.